Okay, let me start. Welcome to class meeting 21 of EECE574, the graduate level probability and random process. We have just taken quiz 2, and around 7 more class meetings are left to the end of the semester. Handouts, lecture videos are available from our primary homepage. Homeworks will be continued to be assigned, so check the PLMS and your email. I will notify you whenever new homework is uploaded. It seems there are nothing to clarify and correct this time, but I have kind of revised the overview of what we are going to cover. Still, we are very behind the original plan. So according to the Populist and Peebles chapter and section numbers, we are covering section 7.4 of the Populist textbook entitled Stochastic Convergence and Limit Theorems. Of course, other than the titles, we have covered many topics. For example, the Poisson random processes and ergodicity and other things that are very, very important. So we have been covered many important topics very, very carefully and a little bit slowly so that you can better understand the material. Anyway, so last time we've covered the kind of some part related to the correlation functions. First one was the positive semi-definiteness of a correlation function. And we also learned some important classes of random processes, such as alpha-dependent random process, M-dependent random process, correlation alpha-dependent or M-dependent random processes, white noise in terms only of correlation functions, not the power spectral density we haven't yet covered, and two similar but very different definitions of mean square periodicity and Y-sense cyclostationarity. And then we're back to the chapter, section 7.4 of the Populist main text. And first, we review the equality of two real or complex numbers. One of the things you'd better remember is that x equals y, if and only if x minus y equals 0, if and only if, strangely, for every epsilon positive, the difference between x and y is less than or equal to epsilon. Got it? So this is kind of motivation of a lot of convergence definitions, like definition of a sequence of sequence of real numbers to the limit, or the definition of Cauchy sequence, and other things. For the approximate equality of two real or complex numbers, the first thing you'd better remember is the bounding technique, even though I haven't covered, and I will not cover in this course. But bounding is very, very important. However, in this course, we will learn the second method, where we construct a sequence of real numbers and show that it converges. So here, if you have two numbers, x and y, and want to claim they are almost the same, then this is not equivalent, but you construct a sequence of real numbers and converges to y. And of course, here, x can be a kind of member of Xn for sufficiently large n. Got it? So this is our trick. And what was the definition of the convergence of a sequence of real numbers? Here goes the definition for every epsilon positive. So here, we just have a magic spell starting with for every epsilon positive. And then the difference is that we have to find some natural number n of epsilon, such that for sufficiently large n, which means that n greater than or equal to n of epsilon, implies the difference between x and here the limit y is less than or equal to epsilon. Here you do not need to always have to put equality, but it's very convenient. Got it? So this was the definition. And the definition includes our target. And this is called the limit of this sequence. And there is another definition related to the convergent sequence is the class of Cauchy sequence. So a sequence, not necessarily of real numbers, it could be complex numbers or some elements in an abstract space. But anyway, a sequence of here, I will limit to the real numbers. A sequence of real numbers is Cauchy, or it is classified as a Cauchy sequence if, and again, we have the spell for every epsilon positive, there exists the n of epsilon, an integer, such that m and n greater than or equal to n of epsilon implies xm and xn less than or equal to epsilon. So here we, here we have the same thing, but the difference is that here only n is involved, but here you have two indices. So if we visualize the difference of the original definition and the definition of Cauchy sequence, it's like if you have some target y and take a small interval of length 2 epsilon. So this is 2 epsilon. Then what does that definition says? Whatever epsilon you choose, you can find n of epsilon. And then after this n of epsilon, then every element, member of x of n, resides in this interval. That is the definition. The difference of Cauchy sequence is that there is no limit. You don't need to know the limit. But here, for every epsilon positive, whatever small it is, there exists n of n. And if you take the max or supremum of xn after this n of epsilon and the infimum of x of n or minimum, then their difference is always bounded by 2 epsilon. Sorry, epsilon. So in this case, got it? So it's strange that such a property results in the convergence of a sequence. So actually, the definition itself does not say that a Cauchy sequence converges. And for the Cauchy sequence to be convergent, we need the space to be complete. And that is a kind of complicated concept at this moment. So I will not talk about that, but just will give you an example. The first example is that you define x sub n, the nth element of a sequence, as, for example, square root of 2 times 10 to the n, and you floor it, and you multiply 10 to the negative n. Then what is x sub 1? X sub 1 is what? 1.4. X sub 2 equals something like that, right? So if we consider only the set of real numbers, then definitely this sequence converges to square root of 2. However, if we only consider the set of rational numbers, these x sub n's are all rational numbers, but its limit does not exist in the set of rational numbers. It's an irrational number. So in that sense, we need actually more than the set of rational numbers. Probably some of you have taken the real analysis course in your undergraduate program, or you are taking, or you will be taking in your graduate program. And the first topic in the real analysis is what? The definition of the set of real numbers. And to motivate that, they talk about what's the problem of the set of rational numbers. And as you see here, if you have a sequence of rational numbers, sometimes its limit is not in the set of rational numbers. So we need a bigger set that includes all the possible limit of out of the rational number set. And the complementing set is the set of irrational numbers. And the union of rational and irrational numbers are called the real numbers. Got it? So we need a set of real numbers. However, in our computer dominant world in engineering, we always need to handle every number as a rational number. But anyway, if the error is small enough, then we are okay. So for most of the engineering students and engineers, we don't need that difficult theory. Almost everything very appeals to our engineering intuition. So that's why some of your advisors will never ask you to take real analysis. But let me tell you, if you want to be a very fine engineer, okay, then probably you'd better take or at least sit in the undergraduate or graduate level of real analysis, and also measure theory and measure theoretic probability courses. Anyway, so here goes another one. So this means that a counterpart saying that every Cauchy sequence is not necessarily convergent. But if we relax the set to the set of real numbers, then every Cauchy sequence in the real set converges. Every Cauchy sequence in the set of complex numbers converges. So it's very good. Got it? The second one is that we should be careful in applying this Cauchy sequence converges in the set of real numbers, because this difference of kind of maximum and minimum or supremum or infimum is sometimes misunderstood by many people. For example, suppose your x of n is square root n, which is definitely not convergent. It's divergent, right? The problem is that you can easily show that the difference of the two consecutive elements of the sequence converges to 0. So in some sense, for sufficiently large n, the neighboring elements, the difference goes to 0. However, the sequence never converges. The reason why many textbooks and I talk about this is the reason why you need to apply a lot of iterative algorithms in developing your estimator, detector, and sum system in real application. So what you do is that you start from some initial guess of the estimate, and you take an observation and update it. But the problem is that you have to have a criterion for stopping. And the simplest criterion would be you observe the difference of the output of the nth and n plus 1's output. And if the output does not change too much, which means that xn plus 1 minus xn is very small, you just stop. But as you see here, the difference between two consecutive sequences converges to 0. However, you haven't yet convergent, and actually it does not converge. So be careful when you make your iterative algorithm stop. Okay? Sometimes the convergence, even though the sequence converges, the rate of convergence is very, very slow, so that you haven't yet convergent, haven't yet made the sequence converge. However, you may make a mistake by let them algorithm stop. Got it? Anyway, That was our topic last time. And today, even though we do not have much time, we ambitiously extend our experience to the equality of two real-valued functions or complex-valued functions. They are not that different. And also, if we have enough time, it's not likely, but we are going to extend the idea to the equality and approximate equality of two random variables. So let's see. First, when do we say two real-valued functions are equal? In order to talk about that, we have to define what is a function. And your high school math or middle school math actually said that when you define a function, you need this standard notation first. So let's say f is the name of a function. Then you put colon and you put some set. And this is called the domain of the function. And you put a right arrow and put the name of another set. Of course, this could be replaced by, for example, an integer. This could be replaced by some, for example, the set of rational numbers. But anyway, what is important is that this is the name of the function, and this is the domain of the function, and this is the range of the function. Now, you have two functions, and you want to compare both of them. What would be the necessary condition for you to say whether two functions are equal or not from this standard notation? First, the domain must be the same. Otherwise, you cannot compare two functions, right? Domain must be the same. Range could be different, but they could be kind of included in a bigger set. So they could be subsets of a set. Got it? So domain must be the same, and let that domain as D. Got it? So let's consider two functions, capital X and Y, having the same domain D in R. So actually, I'd better say this as D to R and D to R. If D are the if the domains are the same, then you are ready to compare whether they are the same or not. Got it? Now, in order to say two functions are the same, what do we need? Here, I said two real functions. Means that this range and that range are subsets of real numbers. Got it? So actually, this is not precise. Probably you want to say R1 and R2. And here, R1, R2, both subsets of real numbers. But anyway. Now, just visualize what you are going to do. Suppose this is the domain, common domain of two functions. And to visualize, probably you will draw the graph of the function. By the way, the graph itself is not a figure. The graph is what? The set of points such that, for example, graph of x, the graph of x is what? The set of x, comma, x, sorry, I used s. Okay, let me use s. S, comma, x of s, such that s in D. Got it? This is the graph of function x. And what is the graph of function y? This is the graph of function y. And if we plot or illustrate, then we have figures. Got it? Suppose this is the illustration of a figure of the graph for x. Then probably you have another one for y. And definitely at this s, let's say S1, and that S, S2, they are the same. However, you will never say these two functions are the same because on the other points S at X in D, the values are different. Got it? So when they could be the same? For every S in D. So definition, X and Y such that the just a second. Yeah, now let me just say this. And R1, R2 in R are equal if for every S in D, X of S equals Y of S. Am I correct? You want to say this, right? If there exists some S0, at least one S0, where this value and that value are different, probably you want to say that two functions are different at that point, which means that they are different. Got it? So in order to claim two real valued functions, here, real means real valued. What does that mean? This R1 and R2 are subsets of R. So actually, here, domain is a subset of R, doesn't matter. Okay, you may say that in this case, two real functions of real numbers. But anyway, so what is important is that here real valued means this part. Got it? But anyway, so the reason why I initially talked about the equality of two real values, two real numbers, is applied here for every S. For example, suppose S is an interval, a real interval like this. Then how many equalities of two real numbers you need to verify, check? Uncountably, infinitely. Because you can replace this value S uncountably infinitely in order to enumerate every possible case, right? So the equality of two functions may be a kind of enormous operation. You have to compare uncountably infinite pair of two real numbers. And each of the pair must be the same. That would be the strict sense, most strict sense definition of equality of two real valued functions. Got it? So this one is in particular called everywhere equality. Because everywhere in the common domain, they are the same. They have the same functional value. So this is called two functions equality everywhere, or everywhere equality. Got it? And this is natural. Now, let's little bit modify this definition as we have done for the equality of two real numbers. So the first one is this one, too obvious. We just replace that part. And some real number equals another real number. Could be replaced by the difference equals 0, or equivalently, the difference is less than or equal to 0, and greater than or equal to 0. Well, that's just logic. However, here goes again for every epsilon positive part. So you can replace this part as for every epsilon positive, the difference between x of s and y of s is less than or equal to epsilon. So you can kind of introduce the strange epsilon positive, but so far it's just okay. Now, we can also talk about that part using a set, okay, set equality. So here, how many equality of two real numbers appear? uncountably infinite in general, unless D is a finite or countable set. We are assuming D is a kind of an uncountably infinite set, okay? So in order to replace this uncountably infinite equality of two real numbers, we use the set equality. Got it? So here goes the trick. So we form a set where two function has the same value. So we restrict the S to a member of the common domain. And among such S, we only take S that satisfies this condition. And if the two functions x and y are equal everywhere on the set D, on the domain D, what would be this set? Equal to the set D. So here we have replaced the uncountably infinite equality of two real numbers to a single equality of two sets, right? This set and the domain, common domain. And you may say that it's just a simple trick. Yeah, you are right. However, this kind of replacement of some statement to an equivalent statement is very, very convenient and important. This I call the lemma, but no mathematical, no people in mathematics will say lemma, but I will just use lemma as a simple consequence of definition. So you shouldn't be confused this lemma as Fermat's last lemma, something like that. Actually, that is that Fermat's last lemma is not a lemma. I think it should be a theorem. But anyway, two functions are equal everywhere. But as I told you, this should be D, precisely speaking, D. And we also replace this one to inequality. So x of s not equal to s y of s. And that is the empty set. And this is just simply that you consider this set S and consider a subset and its complement inside S, right? And if S and that subset is the same, then inside S, the complement of this set would be an empty set. So they are the same statement. Now, here goes another thing that looks interesting, is this. So we replace this part using epsilon for every epsilon positive. So here goes the set of S in D such that for every epsilon positive, the difference is less than or equal to epsilon equals D. You can also, same thing, you can just kind of reverse this inequality, or you find the opposite. So greater than epsilon equals the empty set. Got it? So there are many equivalent definitions. But as I already told you, and you feel this everywhere equal definition is too strong. As I told you, when we were taking signals and systems, we considered a discontinuous function, so-called rectangular wave, right? Or square wave. And we represented that square wave using a Fourier series. Especially, we've studied some strange thing. The Fourier series converges to the original discontinuous function everywhere except discontinuous point. And when it converges to the midpoint of the jump discontinuity, something like that, if so-called Gibbs, Dirichlet conditions are met, something like that. Got it? Now, the Fourier series, even if we have infinite terms, does not converge to the original function, right? However, we as engineers believe that's useful enough. Why? Some of the textbooks says that the error between the signal and our limit function, or sometimes the target signal, the square wave, and our finite truncation of the Fourier series has energy of the error signal converges to 0, something like that. And if that is okay, then we are happy. That is what we learned in signal-gen systems. So definitely equality of two functions everywhere could be too strong. So we want to claim like this. Assuming right continuity for convenience, you would claim x of s equals is y of s, for example, because they are almost everywhere equal, except some points that does not contribute to the error in engineering sense, something like that. So we want to relax our too strong definition of everywhere equality. Then what would be the relaxed version? That is almost everywhere equality of two functions. So here goes the definition. This is different from everywhere equality of two functions, but they look very similar. Suppose you have two functions, x and y again, having the same domain. Now, what you do is that you use the trick of using sets. Okay, so you form a set. The set starts, this is a set of S in D such that x of S and y of S are different. Got it? However, this set evaluated by some strange function called M, that is called Lebesgue measure, probably in our case, if D is a subset of R, okay, then it's 0. What does that mean? And that understanding requires your knowledge of measure theory. However, I believe almost none of you have taken measure theory. So let me just be simple. That is measuring the length of the subset of real numbers. So for example, in the previous example, suppose this is every integer. Ready? Then what is that set? What is the set of S in D? Suppose D equals R, and you have infinite square wave. What would be that set? This would be the set of all set of all rational numbers, right? Now, what is the length of this set of rational numbers in the set of real numbers? That is 0. Okay. So measure of this set is 0 as a subset of real numbers. So you can just ignore the set on which the two function values are different. Got it? So if this set has, where it is? This set, not necessarily empty set, but its length is 0, then we are okay. That is the second definition of equality, and this is called almost everywhere equal. Okay, two functions are almost everywhere equal. Okay, it seems I was too ambitious in kind of measuring our possible coverage of today. Okay, let us stop here and continue next time. Okay, that's all for today.